All right, this lecture is to review how to predict products and balancing equations. All right. Now, if you remember back from honors or regular chemistry, there are 5 types of classic reactions. There are synthesis, there are decompositions, there are combustion, and there are single and double replacement reactions. There's a 6th type of reaction called redox reactions, which we won't get into talking about until the next unit. Okay, so this is still really a review of honors or regular chemistry in which going over reactions. And specifically, the hard part here is I know all of you pretty much can balance equations just fine. What makes it harder is being able to write formulas and mainly to predict products from if you're given just reactants. Okay, so first of all, identification. You should be able to look at the reactants and identify right away what type of reaction it is. If it is a synthesis, you typically are going to be given 2 elements, okay? And they combine together to form a compound. Sometimes you might be given multiple compounds and they just form a more complex compound. But in predicting products, most often it's going to be two elements. Now, usually the element, one of them is a metal and one is a nonmetal. And the reason why for this is you can use the periodic table, or you should know or have memorized the charges in some of these elements or their ions, I should say. So if it's 2 nonmetals coming together to form a organic compound, typically that's out of the range of this class and you would not be expected to know what the product is. They probably would give that to you, okay? But if I turn a page, okay? So by knowing those charge states, we can then figure out what the formula is going to be. Okay, so we bring it together. A synthesis means the elements come together and then they form a compound from it. Okay, there are a couple other classes of synthesis where they're not elements, and that's when we're dealing with an oxide. If we have a nonmetal oxide like carbon dioxide and we bubble it through water, you'll notice that when you have 2 chemical compounds, you typically wouldn't expect synthesis. You actually would expect down here, number 5, double replacement. Because typically when we have 2 chemical compounds, the positive elements switch positions to form new compounds. That's what a double replacement means, if you can remember back to that. The positives switch positions, forming 2 new compounds. However, if you notice here, the carbon-hydrogen could not change positions because we would have carbon going back with oxygen. It's with the same nonmetal. So this cannot be a replacement because it would not have any chemical products. It'd be the same thing. So that right away is the telltale that this could not be a synthesis. Instead, it cannot be a double replacement, my fault. Instead of it switching the positive atoms, it literally comes together and forms one larger compound. In this case, it's going to form carbonic acid. So a nonmetal oxide in water will always form an acid, which means it's going to begin with H, and everything else you literally usually just combined, and that usually gives you the formula of the acid. If it's a metal oxide, like sodium oxide, again, they both have oxygen. It can't be a replacement. So these come together and it forms a base. Well, if you remember back from honors chemistry, a base contains the hydroxide ion. So this is going to make sodium hydroxide. So nonmetals in water, nonmetal oxides in water will form acids. Metal oxides in water will form bases. Okay, it will form hydroxides, and the acids will begin with hydrogen. Okay, to balance this equation, we just need to put a 2 in from the sodium hydroxide, and it is balanced. Letter D, we no longer have. You do not have to worry about complex ion chemistry. So what you have to worry about is the metal and nonmetal oxides in water. The decompositions is pretty much the reverse of the synthesis. Instead of 2 substances coming together form 1, we have 1 substance breaking apart into 2 or more. Again, if it's a binary compound composed of 2 elements, they just simply break apart into its elements. The only thing you got to be careful of is it a diatomic element? If it is, make sure it's diatomic. Okay? The other couple of classes, D and E, is exactly the opposite of what we just talked about. If you're going to decompose an acid, we're going to go backwards. We're going to break it apart into a nonmetal oxide in water. If it's a base, it's going to produce water and a metal oxide. So it's the reverse of that. B and C is just a couple of specific types of decomps that you need to be aware of. I try to hammer this a lot in honors chemistry along with Ms. Fassler, but it's something you might need to practice with. If you have a metal chlorate, sodium chlorate, chlorates are ClO3. If you have a metal chlorate and it decomposes, it's going to produce a metal chloride, sodium chloride, good old table salt, and oxygen. Chlorates, when you heat them, decompose them, they produce oxygen gas. And then to balance it, we need a 3 there, 2 there, and 2 there. Balancing, I'm not too concerned with you guys. I think for the most part, you're fine with that. It's being able to predict and write formulas is where you're going to probably have the most struggles. Lastly, metal carbonates. If it's a metal carbonate, like magnesium carbonate, it produces a metal oxide, in this case magnesium oxide, and carbon dioxide gas. So chlorates produce oxygen gas, carbonates produce carbon dioxide gas. Okay? And in this case, a metal oxide. Magnesium is in group 2. It's got a +2 charge. Oxide is in group 16. It's 2 away from being a noble gas. It's going to form a -2 charge. It's a 1-to-1 ratio. So there's the balanced equation for those. Combustion reactions. Combustion reactions is something plus oxygen. The most common type of combustion is the combustion of a hydrocarbon. Let's look at propane. If we're going to heat propane that's in a gas grill. Combustion reactions is a fuel, a hydrocarbon plus oxygen, and when it burns, it produces carbon dioxide and water. Okay? So you just have to remember, if you are going to burn an organic compound that contains carbon, hydrogen, it can also contain oxygen, it could also contain nitrogen, but for the most part, it's going to be carbon, hydrogen, and maybe oxygen. Whenever you have an organic compound that contains that, it's going to produce carbon dioxide and water. Okay? And then you just got to go ahead and balance it. Single replacement reactions, back in honors chemistry, we had to check the activity series to see if the reaction was going to occur. For the sake of AP chemistry, these reactions always occur, so you do no longer need to worry about checking the activity series. In a single replacement reaction, you have an element with a compound, and because that element is more reactive, because in the sake of AP chemistry, if they tell you a reaction is going to occur, it has to occur. So therefore, A is more reactive than B, and so it replaces B, and we get the new compound and a new element formed. Okay? This is typically when we look at metal replacements, where we put one metal into a solution and replaces another metal that's in solution. This is the most common type of things. It's really a type of redox reaction, and we're really going to see more of this in our next unit when we get into solution chemistry. And then lastly, double replacement reactions. In double replacement reactions, you just have to know that the 2 positive ions switch positions to form the new compounds, and we get the products from there on. Okay? All right, so that's just a quick rundown of the different types of reactions. Again, your textbook does a good job if you need to look back and read some of this, but these are the types of reactions, and the best way of getting better at this predicting product stuff is just to review and do practice. So down below, I've got 10 examples of redox reactions that I would like you to go ahead and do. Pause the lecture now, and then when you're done predicting the products and balancing it, see if you get the reaction right. You do not have to be worried about states of matter. You can just put down the formulas of the reactions and products and balance it, and that is sufficient for this course. Okay, so go ahead and stop now, pause the lecture, and see if you can do the following 10 reactions and see if you get them right. All right, so let's see what you came up with. Sulfur trioxide. Because it's 2 nonmetals, it's a covalent compound, which means there are no charges. Okay, it's 2 nonmetals, so therefore it's a covalent compound, and we use covalent naming rules. So sulfur trioxide is SO3, water is H2O. This is an example way back at the top. This is a synthesis because they both contain oxygen. Sulfur is a nonmetal, so we're going to form an acid. So if I combined all of the formulas, I get H2SO4, which is sulfuric acid. Here's one of the reactions that leads to acid rain. Sulfur trioxides liberated by some coal burning facilities will produce it'll go up in the atmosphere, combine with water molecules, and form acid rain. Methanol. I do not expect you to know how to do the formula of methanol. My apologies. I would have normally had the formula for that. Hopefully you might have maybe looked it up. Methanol is CH3OH or CH4O, however you want to do if you want to combine the hydrogens, plus oxygen. What type of reaction is this? Combustion. It's an organic compound containing carbon, hydrogen, oxygen. Therefore, the products, there's nothing really challenging to it. Carbon dioxide and water. The hardest part now is the balance. One carbon, one carbon. There are 4 hydrogens on the left. We need 4 on the left, so we put a 2 there. There's 2 oxygens and 2 more with the waters. There's 2 in the carbon dioxide, 2 this. There's 4 on the right side. There's 2 on the left, but don't forget about the oxygen in this guy. There's an odd number of oxygens. Whenever there's an odd number of oxygens, we have to come back and double the fuel, which means I've got to change this to a 4, and I've got to double this to a 2 to rebalance the carbons and the hydrogens. Now I've got 2 times 2, I've got 4 oxygens in the carbon dioxide. 4 times 1, I got 4 in the water. There's a total of 8 oxygens on the right side, so I need 8 on the left. There are 2 oxygens in the fuel now because of the 2 in front of the methanol, so I need 6 more coming from the oxygen, so I need a 3. So that was a little bit harder one to balance. For the most part, if it doesn't balance with putting a 1 in front of the fuel, it will if you put a 2 in front of the fuel. All right, bromine. Bromine is a diatomic element, Br2. Again, think of Hofbrinkel. Brinkel, Br, Brinkel. Bromine is a diatomic element. And we're going to mix it with copper 2 iodide. Copper 2 tells me it's +2. Iodine is a halogen. It's -1. And therefore, when I cross drop, I've got 2 iodines and 1 copper. Now, unlike above, what I showed you was a metal replacement. Bromine is a non-metal replacement. If bromine is a non-metal, it's not going to replace a metal. It's going to replace a like non-metal. So now what happens is the non-metal kicks out. So the bromine is going to replace the iodine, forming copper 2 bromide. And because they're both halogens, they're going to keep the same ratio of 1 to 2 with copper. Oops. And there it is. So in a halogen replacement, you've got to replace the negative ions. The non-metal replaces the non-metal. If it's a metal replacement, then the metal replaces the metal. All right, hydrogen carbonate is heated. Be careful, the word is heated. It is not combusted. If they don't use the word combusted, heat is the typical way that we decompose chemical compounds. So this is not a combustion reaction, which some of you might have had. Okay? If you did, no big deal. But for this case sake, heat it means just to decompose. And when you do, you'll notice that we're decomposing an acid, which really is up above, is the opposite reaction that we did up above. When acids decompose, you're going to get a non-metal oxide, which is going to be the non-metal, not the hydrogen or the oxygen. So in this case, carbon. It's going to be carbon dioxide and water. Carbonic acid is the most common acid. It's found in soda pop. When you open up a can of soda, the reason why I hear the ka-ch is the pressure releases, and the bubbles is carbon dioxide gas. It's a carbonated beverage. All right, iron 2 sulfate. Should have been a formula of FeSO4 Sulfate is -2, iron is +2. Ammonium sulfide. Sulfide has got a -2 charge because it's in group 16. It's 2 away from a noble gas. Ammonium is the most common positive polyatomic ion. It's got a +1 charge, so therefore it forms a ratio of 2 to 1. This is an example of a double replacement because sulfate and sulfide are different negative ions, and therefore they switch. So we are going to get iron 2 sulfide and ammonium sulfate. Okay, simple double replacement. Just make sure you've got the charges of the ions. Calcium chlorate is heated. Chlorate has got a -1 charge. Calcium is +2, so we need a 2 to 1 ratio. Again, it's heated, so it's decomposed. This is the decomposition of a chlorate, and if you look above, what do they decompose into? A metal chloride, in this case calcium chloride. Chlorine is a halogen, it's in group 17, it's a halogen, it's got a -1 charge. Calcium is +2, so we need a 1:2 ratio when we cross drop, and we're going to get oxygen gas. To balance, we need 6 oxygens on the right to balance the 6 on the left, and we are done. Magnesium hydroxide is heated. Hydroxide is the OH ion. It's got a -1 charge. It's a polyatomic ion. Magnesium is in group 2. It's got a +2 charge. So we have the formula given, 1:2 ratio. Again, heating means really to decompose. Now we're decomposing a metal hydroxide. So I'm going to get a metal oxide, in this case magnesium oxide, and water. And that is an example of a metal hydroxide, which again is the decomposition like above of a base. When we decompose bases, we get a metal oxide in water. When we decompose an acid, we get a nonmetal in water. Potassium carbonate. Potassium is in group 1, +1. Carbonate is a polyatomic ion that has a charge of -2. So we have to cross drop. There's got to be 2 potassiums to balance out the charge of -2. Magnesium chloride. Magnesium is +2. It's a group 2. Chlorine is a -17. It's a -1. It's a halogen. So we need a 2:1 ratio. Again, the negative ions are different, so this is a typical double replacement. The magnesium and the potassium are going to switch positions. We're going to get potassium chloride. Be careful here. A common misconception is students want to put 2s here, but the 2s are there on the previous side, the reactive side, because of needing 2 of them to balance the charge. So because these are both +1 and -1 ions, we just need a 1:1 ratio. Okay, the other compound is magnesium carbonate, which is also 1:1 ratio because they're both the same charge, +2 -2. To balance, all we need is to put a 2 out in front, and there's our chemical reaction. All right, zinc and sulfur, this is 2 elements. If they're 2 elements, the biggest thing, first of all, is either zinc or sulfur diatomic. They are not, okay? So this is nothing more than a typical synthesis. Zinc is a metal. It has a charge of +2. Sulfide is in group 16. It's 2 away from a noble gas, so it wants to gain 2. So this is going to form a 1:1 ratio. Right there's the reaction, zinc sulfide. Hydrochloric acid, HCl, plus sodium carbonate. Sodium is +1, carbonate's -2, so again we need 2 sodiums for every carbonate. Hydrochloric acid, hydrogen is +1, chloride is -1. Hydrochloric acid, most of you already have the memorized formula, HCl. Again, this is a double replacement reaction, so if I switch the positions around, I'm going to get sodium chloride and hydrogen carbonate. Again, when formula I write, I always write 1 of each, and then I check charges. And I'll notice that the sodium chloride is NaCl because +1 -1. The hydrogen carbonate, however, the hydrogen is +1, group 1 family, carbonate's -2, so I need 2 of the hydrogens to balance. We have 2 sodiums on the left, so I need 2 on the right. That gives me 2 chlorines on the right. I need 2 on the left. It gives me 2 hydrogens on the left. There are 2 on the right, and there's 1 carbonate on each side. We are balanced. So that's a review of balancing reactions. Like normal, it's hard to get a AP lecture in 15 minutes. I try to do my best. But now I have some extra additional problems. I strongly recommend doing them each day. Like I said, try to spend a half an hour at least a day on doing practice problems. This is where I tend to worry a little bit. I'm hoping my students are doing enough at home that they're getting enough practice so that when they take a quiz or test, they're really proficient at it. Those of you that are doing that, great, keep it up. If you're not, try to start doing that now. You're really going to start to see the material get a little more difficult, and you've got to make sure you do the practice problems. So go ahead, try the practice problems. I have submitted an answer key with it, and let me know if you have any questions on reactions. sketched a periodic table. If you have a metal, remember, a metal is any element that is to the left of the red staircase. The nonmetals are only along this area right here to the right of it, and we have the metalloids that follow on the staircase. For the most part, if it's a metalloid that's to the right of the red staircase, it's most often thought of as a nonmetal. If it's on the left side, it's most often thought as a metal in naming chemical compounds. Okay? So when you have a metal with a nonmetal, remember, metals give electrons to nonmetals, and therefore the metal, I'll give it as an X, the nonmetal is Y. The metal is going to have a positive charge, and the nonmetal is going to have a negative charge. The position on the periodic table can be very useful information in being able to identify or predict a typical charge state of the metals. Any element in group 1 is going to have a +1 charge. Any element in this vertical column right here is going to have a +1. And that's because they share one commonality, and that is that they are all have one valence electron. Hydrogen, while it's in group 1, which we call group 1 again, if you remember, group 1 is called the alkali metals. Hydrogen, while its position on the periodic table is above that, the purpose of that position is because it has one valence electrons like the rest of the elements. But hydrogen is not a metal, it is a nonmetal. So make sure you're aware of that it's the only element to the left of the staircase that is really a nonmetal. Okay? Its position is due to electronic configuration. Elements in group 2, the next vertical column, these guys all typically have charges of +2, always. So if it's group 1, it's always +1. If it's group 2, it's always +2. If it's in group 13, and again, to be a metal means it has to be below. Okay? It can't be that element, which in this case is boron, which is a metalloid. You don't typically see boron forming compounds for the sake of this class. If it does, it's usually an organic compound. So the metals are going to be below that red staircase, and these elements typically are +3. Probably the most important one of that set is aluminum. Aluminum is a metal. It is not a metalloid. It's the only element on the staircase that is not a metalloid, and aluminum is the most common +3 particle that has a metal that has a charge of +3. Okay, there are some others in that row, but aluminum is the most common one. Group 14, a few of these have got +4 as well. Beyond that, they usually aren't typically included on the national exam. If they're in the D block, the transition block of metals, these elements tend to either have +1 or +2. They can have other charges, but typically they're 1 or 2. But remember, if you have an element in a D block, let's say it's like copper, they'll give you extra additional information because they'll say copper 2. That tells me that the charge in that copper is +2. Okay, so that information will be given to you. The nonmetals, it's opposite. When you have a nonmetal, they tend to form negative ions. They only need a few more electrons. They have high coulombic attractions, therefore they want to gain electrons. The noble gases, these elements are non-reactive, so they don't have a charge state. But if you have the halogens in group 17, they're one away from being a noble gas. The halogens are always +1. Fluoride, chloride, iodide, -1. The next family next to it, group 16, -2. The oxygen family, oxide, sulfide, selenide, -2. And group 15 would be -3. Specifically, most common, nitrogen, nitride. Nitride is -3. So the position of where the element is, in which family it is, that tells us its typical charge state for monatomic elements.